Okay, let's get started. So now that we've sort of figured out, who's registered for the class and some introductory topics, we're going to be going on into some other topics of machine learning where, knowledge of the prereq is really going to matter. So we're giving you sort of as a courtesy tutorial. This will not really replace semester-long course on the analysis of algorithms or semester-long course on linear algebra, and on Thursday we're going to do probability. But we just want to make sure that people are up to speed for the rest of the class. So we're going to start with analysis of algorithms. So this is really important. If you have an algorithm whose runtime is n log n, where n is the size of the input, versus polynomial, you're going to have a much better runtime if it's logarithmic or n log n. And this curve, the polynomial curve, is upper bounded sort of by the exponential curve, which goes at an even faster rate. So it might be okay when you have a little bit of data or small inputs, but as your data gets larger and larger, we really care about the asymptotic performance of your function. That's for running time. In machine learning, we're usually talking about things like n might be the number of examples to reach a fixed error rate. So those are the kinds of analyses we might see. But in general, we need to know about the growth of functions, and here are just some examples of how exponential time is much faster growth rate than any polynomial, which is faster than n log n, faster than linear, which is faster than log n. So, in general, we want smaller growth time. Okay, so this seems like a good motivation, but we actually have notation. We have mathematical definitions behind our asymptotic notation. So at a high level, without defining them yet, you can basically think of big data essentially meaning that equals in terms of growth rate. You can essentially think of big O as a less than or equal to, big omega as a greater than or equal to, and then we have little o, which you can think of as strictly less than, and little omega, this is lowercase omega, which is essentially strictly greater than. Where what we're comparing is growth rates of functions. So let's define big O, big theta, and big omega. So what we're saying is we don't really care what happens. So for big O, we don't really care what happens at first. But after some n, that we're going to call n naught, f of n is always upper bounded by G of n, or at least C times G of n, where there exists some to make that whole. So we might need actually light on the board. So if we have some function G of n, then the set of functions known as big O of G of n are functions such that there exists some constant c and some constant n, these are both positive, such that basically this left-hand picture holds, right? So such that f of n is always going to be upper bounded by c times g of n. For all n above that threshold and not. Okay, so that's what we have said over here. So g of n forms an upper bound on f of n. Okay, and we have a notation. So this is a set, right? So I've defined it with curly braces. So this thing is a set. So we can have a function being in the set. Okay. So there's lots of examples. In general, you'll need to be able to look at a function and check whether what its big O upper bound is. But so, for example, this is in various sets, but for example, it's in big O of n cubed. So I'm gonna fix the c to be 1 for this to hold, and at what n naught does this start holding? It does hold for that. Can you give me the smallest one?
2.
Right, so this holds for all n greater than or equal to 2. So if c equals 1, 2n squared equals n cubed at n equals 2, right? That would be that intersection point. And then after that, n cubes are always larger. Okay, so let me give examples of functions in O(n) squared. Okay, so certainly n squared is, but if we add smaller polynomials, we're still in O(n) squared. Okay. Even if we multiply them by really large constants, we'll be able to find a constant and not such that this has a faster, this has this function is bounded by this asymptotic rate. And then also smaller things. So if you have n to the 1.999, for example. So this is an upper bound. On growth rate of the f of n's in this set, right? So you say at most. You don't say at least for this one. It's an upper bound. Okay, so this language is also kind of important, like if you're interpreting someone just explaining the running time or if you're reading a paper. So we're saying growth rate of f of n is at most O g of n. Okay, you can't say at least when you're using big O, because big O is an upper bound. We'll get to the one where you can say at least. Okay, so this should be a review, but feel free to stop me with questions. So the reverse of this, so we said, we've done this one here, and we said that this is like a less than or equal to. So in contrast, big omega is similar to a greater than or equal to in terms of growth rates of functions. And so here, the comparator function is g. We're trying to lower bound the growth rate of f. And basically there exists some n naught and there exists some c that for n greater than n naught, fn's growth rate is always lower bounded by c times g of n. So again, it's a set. Okay, so do some examples. Let's do log base 2. Okay, so this can be seen, for example, with c equals 1 and n naught equaling to 16. Right, so we have square root of 16 is 4, and which equals 16 times log base 2 of 16. Oh, sorry. Right, which is equals 4. And as we take any n greater than 4, the square, as we take any n greater than 4, the square root will now be larger than the logarithm of that n. Okay. So that means we cross it here at n equals 16. All right, if we take any n greater than 16, its square root is going to be greater than its log base 2. So the crossing for that function is where we have root n here and log n here is n equals 16. 16 when we're using base 2. So we can do examples of functions. So again, this is a set. And so we have some gn in here. Say we have n squared. So with appropriate choices of constants, we can lower bound all of these. Etc. Okay, and then we can arbitrarily multiply by really large constants, and that'll just, change what constant we choose for our C. So we might be in a situation where Fn can be sandwiched between Gn by using two different constants. So this is only the case if Fn and Gn have the same asymptotic growth rate, and that's big theta notation. So remember, this is sort of like equals. We're saying that they have equal growth rate. And in terms of sets, omega of G of n is just a set intersection of big O of G of n with big omega of G of n. Okay, so we defined these already as sets, and I erased one of the set definitions, but we have both the set definitions, and now we just need to check their intersection to see if a function Fn is in big theta of G of n. So basically, if for the same G of n, both this property and this property holds, of course you're going to need different C's. For some and not, you'll choose the higher and not of these two where it holds, where the and not where they both hold. That'll give you this and not. Then they have the same asymptotic growth rate, and there's theta of Gn. Okay, so I told you to take the intersection of the sets, but we can also write it out. So we need two constants and some n, such that we get Fn sandwiched between Gn. Okay, so this picture. So this is not usually the case. They have to have the same asymptotic growth rate. This is sort of getting into, you can kind of see them from these examples here. Okay, so you're going to have two different constants. I forget how I labeled my constants. Okay, so maybe to make it easier, I'll have the higher constant have a higher subscript. Okay, so you just have to check whether this can be done for two constants. For this particular function, we have the following. Okay, so we have this function would be 8 squared over 4, and the upper bound is 8 squared over 2. And then we have a half times 8 squared times 2 times 8. So we get, 32 minus 16. So that's why we're just going to sort of, when you have a polynomial function like this, where you have n to the 2 and then n to the 1, whether it's added or subtracted, we just need to look at the first term, and that's going to give us our growth rate. So that's why those examples came up both for big omega and big theta, because it's big omega of n squared with the appropriately defined constant, and it's also big O of n squared with the appropriately defined constant. These two constants are different. That means that this function has the asymptotic growth rate of n squared. So any questions? Sometimes you're going to see statements where you have kind of an anonymous function. You're going to say something like fn equals n cubed plus o n, for example. So this is an anonymous function in the class on. So this means it equals n cubed plus h of n for some hn that has this growth rate, i.e. linear in n. So we go from existence statements to a for all statement for our C when we want to make the bound tight. So I told you that so if we want strictly less than or strictly greater than. So omega was sort of like strictly greater than. Was like greater than or equal to. Lowercase omega looks like this, and this is like strictly greater than. So we just rewrite the set, but this C becomes a for all. And actually, we don't have slides with this. So we can still now per C there can be a different n, that's fine. And then the bound is tight. Fn is strictly greater than Cgn. Okay. So is n squared in little omega of n squared? Well, this might be hard to reason about, but you're not going to be able to lower bound this strictly for every value of C. So for example, C equals 1 breaks that. And you're looking at a for all statement. So no. Even though n squared is big omega of n squared. And so if we look at, say, n to the 2.0001, that is going to be little omega of n squared. Okay, this is a strictly higher growth rate. Or even if we look at n squared log n. Okay. So these have strictly smaller growth rates than what's on the left-hand side. And then we have the same idea for big O, which is little o. It's a little harder. You have to check the size of your O, which is particularly hard in handwritten stuff. So big O is an upper bound. Little o is a strict upper bound. So the set little o of g of n are functions where for all constants there exists a threshold and not such that. So this is exactly going to be the same as the statement for big O, but we have a strict inequality and it holds for all c. So Fn is strictly less than Cg of n for all n greater than or equal to n0. Okay, so we have things like n to the 1.999 little o of n squared. Right, n squared is not little o of n squared, but it is big O of n squared. So we might try to reduce it by using constants. But that doesn't hold because remember, we have to have this hold for every constant. So we can choose the C for which strict inequality still breaks. Okay. That was essentially the review of asymptotic notation. If you're feeling at all fuzzy on this, because this is just sort of the beginning part, look at the chapter 3 of the algorithms book. So I think you use CLRS, Corman, Leiserson, Rivest, and Stein, the big white book, or green or blue, used to be white. The heavy algorithms book for 6212 or 3212. These were just some introductory notations, but the way these things behave, symmetry, reflexivity, etc., you might just want to brush up on that by looking at the beginning. I think it's chapter 3. Good questions so far. I'm using a bunch of different notebooks here. Okay, so sometimes the reason why you don't know what the growth rate of your function is that it's given to you as a recurrent. So you might get some f of n you might be given some f of n, or t of n in this case, in terms of values smaller than n. Now it could be n divided by something, it could be n minus something. And here there's going to be some rest of your function here that we replace by f. So you're asked to find the growth rate of t of n, but t of n is only stated to you recursively. Or you're looking at your own code is recursive, so you don't know its growth rate. For that, you should look up in the beginning of CLRS, I mean, unless you're going to memorize this master theorem, which for any constant here, any function here, and, well, yeah, so for these sorts of functions and this form of f of n, based on the relation of f of n to these constants, it's going to tell you what your growth rate is. Okay, so this is just another, for those of you that have missed the prerequisite, this is another important resource. It'll be on this slide, but it's also in the CLRS book. So this helps you analyze recurrences. So your recurrence might be for the running time, it might be for some property of your algorithm. And also, it's important to be able to bound summations. This is another thing that you can really just look at the beginning of CLRS for. Okay, so this is very helpful if someone says, you know, what's the sum of the first n numbers? So the sum of the first 4 numbers, for example, all I have to do is take 4 times 4 plus 1 and divide by 2. And this happens a lot, like if you're trying to analyze the running time of your algorithm, you might have these sorts of forms. The other thing you might have is the sum of 1 over the first n numbers, and you're going to end up getting log of n plus something that's linear, and so this is big theta of log of n. Okay. The geometric series is also very important. So sometimes if the lectures are kind of advanced and some math steps are skipped, if you're looking for something that might be skipped, it might be one of these series or might be some of the other series that are bounded in any intro algorithm text. Okay, so that's another thing that you should just make sure you know how to review those things. Okay, and we've also been, so let me free up some space here. We've also been throwing around logarithms already. Let's just do a quick review. Also for that, there's a lot of places you can review logarithms, but for example, it's in the beginning of the CLRS book. So we liked logarithms because they had those really slow growth rates, sublinear. So that would be important for the running time. It would also be important if you want to show, for example, that your error rate is only logarithmic in a number of examples for good machine learning, for example. Okay, I'm not going to give exhaustive properties. One thing that is really helpful is change of base. So you might have log in some kind of base, but you can get to any other base. So A, B, and C all have to be positive. And also, generally, that we think of the bases being at least 1. So this thing, log C of B, this is just a constant. So I've taken log in one base of A to log in another base of A by multiplying by a constant. And so how does multiplying by a constant affect the asymptotic growth rate? Right. Remember, multiplication by a constant does not affect the asymptotic growth rate. What do I mean by asymptotic growth rate? Which family your function belongs to? Does it belong to big theta of n squared or big O of n cubed, etc.? So what this means is that when I say log, it doesn't matter if it's, log base 10, log base 2, log base p, which is the natural log, with respect to the asymptotics. Because I can move between all of these by multiplying by the appropriate constant. So we'll just say log. When you care about the actual constants, then it matters. Generally, we're not going to use log 10 much in this class, but we're generally going to use natural log and log base 2 pretty interchangeably because of this reason. Okay? Because if you just care about the asymptotic growth rate, you just need to multiply by 1 over log base, the new base of the old base. Okay? And what I mean by a constant is this denominator is not a function of a. Right? I'm taking the log of a number a, and I can just swap the bases by multiplying by something that's not a function of the number a. Okay, so I'll drop the base in some of these. Log of 1 over a is negative log a. Log of a to the n is n log a. So various things that we'll be using. Various bounds that might come in handy. But anyway, these are all in the beginning of CLRS, around the first 3 chapters. Log of 1 is 0. Okay. So again, just to give you, we are going to use things like this a lot. If you have a product, it's the sum of the log. Okay, so just to get back into being familiar with these things, we may need to review. Okay, so any questions? In analysis of algorithms, I'm basically encouraging you to review asymptotics, how to compute the asymptotics, so how to compute the growth rate of a function. Your function first might be recursive, so then you have to get it into a form that is just a functional form that's not recursive, and then you should be able to answer, is it big O of this, big omega of that, little omega of this, etc. Sometimes to get a handle on a rate or something that you're computing, you'll need to bound a summation. And in general, we're going to use logs a lot. They come up in probability quite a bit. So these are things to review from algorithms. Any questions about any of those? Okay, we'll try to do a whirlwind taste of linear algebra. And then next time we'll do probability. Also, I posted some really good review sheets for linear algebra. I'm going to post the probability one. I think I posted, I think the ones I've mostly posted are about linear algebra, but there might be some algorithms reviews. So those are under the readings. Okay. So a lot of what we first need to do is establish notation. We probably will mostly only go through notation and some multiplication properties. And then there's a lot more advanced things you can do that are on the review sheets that I posted. And so these things like an orientation of a vector really matter, and you'll also see this when you start to play around in MATLAB. So we're generally going to, when we define a vector, we're going to define it as a column vector. So we have these scalar values in a column, and there's d of them. And it seems like it shouldn't really matter whether this is a column or a row, and it's true it won't in some computations, but we like to be precise here because we want to specify when we're going to need the transpose, etc. So X transpose is going to be a row vector. It's just the same element listed in a row. In MATLAB, you use a single quote to get the transpose. Also, simultaneously getting a really good feel for linear algebra and a really good feel for MATLAB is really synergistic, because MATLAB allows you to reduce tons and tons of for loops because there's great support for linear algebra manipulations. Okay, so for most vector and matrix multiplications and that sort of thing, you're not going to be needing to write for loops. You can, it'll work, but you know, try to get a sense of linear algebra manipulations that you can do in math, and note that with the proper notation, MATLAB is going to support those. Okay. That's actually one. I guess some people have wondered why MATLAB is used so strongly in machine learning. I think that's one of the reasons. Okay, so some basic things that some of them we've already done. So let's just start with some facts about vectors, and then we'll do facts about matrices and multiplications, etc. Okay. So you can either write this as X transpose Y, so given column vectors of length D, X and Y, or you can write it as X dot Y. I think MATLAB has a function actually called dot, right? But you wouldn't necessarily need to do that. You, yeah, I forgot how it works in MATLAB, but yeah. Go to sections, go to so you're probably used to it, but just in case, we're just doing a scalar multiplication between the ith element of the two vectors, and then we're summing that over the indices. And the other thing is MATLAB, the index of vector starts with 1 to make it a lot more like linear algebra, whereas most data structures that you might use when you use an array and other programming languages, their index starting at 0. So you're not going to have to worry about that with MATLAB. Okay. And then we went ahead and talked about the Euclidean norm. So some of this should be a review. So this is taking the square root of the dot product of x with itself. Okay. This has a geometric interpretation. What is the geometric interpretation of the Euclidean norm of a point x? Yep. So think of x as a vector. So in two-dimensional space, if d equals 2, if we have a point, say 2, 1, then that's a vector, and the norm of it is going to give us this length. Okay, so this is the vector, and we're interested in this length. Okay. So if you have two vectors x and y, then the angle between them is going to be their dot product divided by their length. So this is the angle between the vector x and the vector y. Okay, so that's why the dot product can be viewed as a way of computing the similarity between a pair of vectors. By the way, so for those of you that have had more advanced math, in Euclidean space, the inner product is a dot product, but in other spaces, it can be defined differently. This is a more general term. So dot product is a measure of similarity between these two vectors. Okay, so what does it mean if x dot y equals 0? Sorry? Yeah. So perpendicular might work on the plane. In general space, we call that orthogonal. What if the absolute value of x dot y equals 1? Actually, not 1. The product of their norms. So they're actually collinear. Okay, so you know, if it's if x dot y is negative this quantity, then they point in opposite directions on the same line. If x dot y is positive in this quantity, positive equal to this quantity, then they just point in the same direction. And we can go ahead and prove the Cauchy-Schwarz theorem, which we talked about before. So we've seen this before. We used it in the perceptron proof without really talking about it much. Okay. So the proof actually relies on this, which we didn't prove, but now that we have this, we can use it. So, right, the cosine is, remember this is another notation for the dot product. So the cosine is defined as follows. I can go ahead and now take the absolute value of both sides. And also, what's an upper bound on the absolute value of cosine? 1. Cosine varies between -1 and 1, so its absolute value is at most of magnitude 1. So we have 1 is greater than or equal to this thing. These norms are always positive, right? The square things, add them up, and take the square root, always positive. And we're done, right? So we proved it from this statement. Okay, so now we can use this in machine learning, as we're going to go ahead and do, for example, in the perceptron convergence proof. I'm not going to prove this again, but another thing that I showed last time that you may need, or I showed some other time, you need other times. So to show this, all you're going to need is the definition of the Euclidean norm, and so we often use the Euclidean norm squared because that's just the dot product, right? Euclidean norm takes the square root of it. Okay, so we've done a lot with one-dimensional matrices, aka vectors. We can now move on to matrices. Any questions with these basics on vectors? Okay, so we have very similar notation, but we'll have, more. We're allowed to have more than one column. Although this is an n×1 matrix, but we want to be able to generalize to the number of columns being more than one. So what we've said is that there has to be n rows and d columns. So we're going to have a bunch of entries, and in the first row, things get indexed with is 1 here, and the first column, they get indexed by a 1 in the second subscript. So everything in the first column has a 1 in the second subscript. Everything in the first row has a 1 in the first subscript, but then you have to have a column subscript. Thanks. So there's d columns, so this element is in the first row and the dth column. On the diagonal, we're going to have these elements where the subscripts match, etc., and then we're going to have dd here. Oh, sorry, yeah, and thank you. Okay, so what about the transpose? Yeah, so what is the ij entry of the transpose equal to? So this is just an entry-wise definition. So I looked at the jth row of M and the ith column of M. So I just need to take this whole thing and switch it around. And yeah, so if this was narrower here, this one is going to be narrower here. So this is N, and this is D. Here, this is N, and then we have D here. So there are special matrices where we would yield a DD here instead of an ND, known as square matrices. And with those, we can talk about symmetric. So a symmetric square matrix is, so we'll have matching dimensions, and we have that Mij equals Mji. So is there anything else we can say with some of the things that we've defined? So for example, the transpose of M will equal M if the matrix is square and symmetric. There's a special matrix. So this is, so in the square case, this is basically just a Kronecker delta function. So we'll see these later in multiplication. These are just like multiplying a scalar by 1. If you multiply a matrix by this matrix I, you get back the same matrix. So questions so far? So we can build up multiplication by starting by multiplying a matrix by a vector. So we start with a column vector. So we'll have to be n by d here. So that we'll have a row of length d for each row. Okay, so this was what we drew before. And now we're going to take the dot product. So for each entry, let's call this y. So y sub I is we take the mth row and we just dot it with x. So in other words, just our definition of dot product. So now we have over the column j equals 1 through d. We have Mij times xj. So this allows us to move up to multiplying two matrices. So, by the way, this is completely undefined if the number of rows of X is not equal the number of columns of D, right? Because I'll have a mismatch here in the dimensions. So for matrix multiplication, we have to have that inner dimension matchup. So if this is matrix M and this is matrix X, we can do this multiplication, but if N does not equal D, then we cannot do X times M. This inner dimension has to match up. Okay, so if we did have M that was N by D, and say we had R that was D by E, for example, then we could do the multiplication. And so all I've done is, I'll do it over here. I have a whole bunch more rows. I mean, a whole bunch more columns. So, and I'm just going to denote them by R. So each, so now I have a vector, a resulting vector for each column of the output. So each of these is going to be M times the appropriate R. Right. Yeah, columns. And we had a formula for that before, right? That would be Mi, each element in MR1 would be M times M dotted with R1. So for each element, M1 dotted with R2, M2 dotted with R1, etc. So this gets to be cumbersome. We can just give you the formula here. So again, these inner dimensions have to line up. Okay, so the only thing that has to line up is D, which is the number of rows of R and the number of columns of M. I don't know how helpful this intuition was actually, but this is the formula. Okay, and this is going to be a review, and also you don't actually have to implement this with for loops because you have MATLAB functions to do this, but you're going to get exceptions being thrown if you don't have the inner dimensions lining up. So in particular, this is what we mean, these have to line up. Okay. With square matrices, you just have to make sure that the dimensions are the same. So matrix multiplication is not the same as multiplying two numbers. So all the rules that we thought we knew for multiplication, some of them hold, some of them do not. Okay, so we have some things like associativity still holds. Now this is where, so we have to have, let's have M is N by D, R is D by P, so MR is what dimension? N by P. So this inner dimension is just what's used for the multiplication, and then you get these outer dimensions. So if that held, let's see, so now we'll define Q to be P by little q. Then we can do associativity. So first, we have to multiply in a way that's legal. So assuming that we've done something like that, we can change the order of the multiplication and still be okay. Because for example, when we multiply n by r, we'll get a matrix with P being the number of columns. So we can multiply with a matrix where Q is the number of rows. But we only have certain distributive laws. So we could multiply in a left distributed way. But sort of, if we wanted to do other types of distributive laws, we have to make sure that the dimensions line up. So these are legal if we now multiply in a right distributive way, because we, oh, actually, yeah. Yeah, I think these are both fine to do RM plus QM.
Find the dimension of R and Q, where else the additional one is down.
Yeah, this is. Whoa.
R and Q are the same dimension that associate the distributive property of.
Yeah, these will at least hold for square matrices, but yeah, let's not do these for now. These are going to be contained in the review sheet. Just check that the dimensions hold. So this does show that it breaks your intuition about standard multiplication. You can always multiply through by scalars. That's not going to really affect anything. The other term that we're going to be throwing around a lot is linear combination. Okay, so we're going to have now a set of vectors, which could be, for example, the columns of a matrix, doesn't have to be. So we have a set of vectors, and we can talk about a linear combination. Where we're just combining them with scalar coefficients. So these just have to be real values. So then we can talk about linear independence. So we start with a set of vectors. Actually, So it's a very special property. So if none of these vectors can be written as a linear combination of the other set of vectors, then they're linearly independent. Okay, so this is the definition. So then we can talk about a span. So say we have n linearly independent vectors of length n, so in Rn. So the number of vectors matches the dimension of the vectors, and they're linearly independent. Then they span any n-dimensional space. So all vectors in that space. So all vectors in that space can be expressed as linear combinations of this set. So this gets us into notions of dimension. We'll probably do a little bit at the beginning of next time about the column space, because we want to be able to define a rank of a matrix, which is going to be a function of the space that their columns span. But I'm out of time, so we'll continue on.